So we have a question that's asking, do you need a parallel compressor for each compressor on the rack? The answer to that would be no. We have two here because it works out nice and tidy. We've got two evaporators, so we size a compressor for each evaporator, and then parallel compression. We were a little above what one compressor could handle, so we added a second one. But you're basically going to do a calculation by people smarter than myself, and they're going to determine the amount of flow that will be a gas or that'll flash off in high ambience, and you'll size the parallel compressors for that amount. So you're going to size them based on the system load. And to answer the question simply, there wouldn't necessarily be a relationship between number of compressors. Is the high pressure valve an end of life product now? If so, what will replace it? Just the receiver valve? Okay, so there has been some confusion around that. We had a controller called the 326A, and for a lot of years it was the only controller on the market that would control a high pressure valve. It's made by Danfoss. That particular controller has reached its end of life and is no longer available. We have a replacement controller for that, which is our pack controller, the 572 model. It's not a drop-in replacement, but the kit that we sell comes with the transducers you'll need, the temperature sensors. But the valve itself, to answer your question, it's not going away. And on a transcritical system, it kind of can't go away because it's what gives us liquid to send to the evaporators. What's the best way to charge a CO2 system? So that's an excellent question. So charging the system, the first consideration is that CO2 below roughly 60 pounds per square inch would be in a solid state. It forms dry ice. So if you pulled a vacuum on a system and you took a tank of liquid CO2 and you just started dumping, you're going to form dry ice inside the system. So you have two tanks for CO2. You have a vapor tank and then you have a liquid tank, and the liquid has a siphon tube down to the bottom of it. So you open your valves. We would open our high pressure valve. We'd open our receiver bypass valve, our expansion valves, and you want to charge the system with vapor up to roughly 100 pounds so that you get above the triple point and you don't make dry ice. Once you're above 100 pounds, you would then add liquid to the system, turn on one of your evaporators, and you get some load going, and you continue to add liquid as the store side of the system, the evaporators take it away. Keep charging with liquid, get your compressors running. Once you've got the entire system down to temp on all your low temp load, all your medium temp load, you continue charging the flash tank until you're above the bottom sight glass, and then the system is charged. So I hope that answers the question, but it's really important that you don't put liquid CO2 in a system that's below 100 pounds of pressure. Are you using the low temp evaporator? Okay. So they're asking if you're using the low temp evaporator as a box or is it used for refrigerant temperature control? So if the question is about the big red here, about our training unit, it's walk-in box, this is actually medium temp. We didn't really have room in a 20-foot container to put either a low temp load or low temp compressors. But this is just a walk-in box. We've currently got it running at 35 degrees, pulled down to temp, so the system would run for today's training. Temperature control, I think I caused confusion earlier when I mentioned we have a shelf to put gas cooler discharge heat into the box. We do that so to get the system to run. If we want to keep compressors running during a presentation, we slide that open. So we kind of use this for load control. But CO2 in general, a transcritical system, think of your walk-ins and your cases as the same way you operate with HFC. You're just going to have an electronic expansion valve instead of a mechanical expansion valve and a case controller per case. The red and green lights on the flash tank, if we're talking about what I'm pointing to here, this is basically, it's tied to a switch. Can we get a close-up? That's actually, I've never been asked that. Great question. With CO2, one of the safety considerations with the high pressure, you have pressure relief valves on your suction header, your liquid line, your discharge line. They all go to a common header via flexible hose, and then that is piped over and outside of the store. For us, it's just outside the unit in this stainless steel piping. And we have a digital contact here to let us know that that's been installed or not. If we don't have this installed, the unit won't run. So the red and green light you saw is turned on and off by this. When it's connected and safe, the light is green. If it's disconnected and unsafe, the light will be red and the system won't run. So it's kind of a dummy light to tell me, hey, dummy, you need to connect the relief valve piping. So we got another great question. How do you avoid bursting the pipes? So with CO2, I got a question yesterday from the audience here at a training. They asked the question, can you keep your existing cases? Can you keep your existing field lines? And really the answer to that is no, because CO₂ operates at much higher pressures. Your HFC piping is not going to be rated. Your low temp side of the system is going to have safeties on it at roughly 59 bar, some for 45 bar on low temp, but it's going to well exceed what you would have. So the shorter answer to your question is that CO₂ requires thicker wall piping, more robust compressors. You avoid bursting piping because you have to replace it with piping suitable for the pressures that are experienced in CO₂. Typical system customers run receivers at minimal capacity. CO₂ charges at 100%. So CO₂ actually, it doesn't charge to 100%. We charge the liquid line out to the store feeding all of our evaporators to 100%, but this only gets charged up until it's above this line. So when I charge this particular system, when I come meet it at various training sites, I literally do what I said earlier. I'll make sure it's above 100 pounds with vapor. Then I will connect to this port here and start charging with liquid. And then I just look in the sight glass here. If you can look in there, and you kind of see a little river. I don't charge it all the way up because I want it to have some turbulence where I can see that I'm at the very top of this line, which is how I simulate being above the bottom sight glass. So the balance of the flash tank from that point up will just be vapor, if that answers your question. So this one's probably charged to about 30% to get it above the bottom sight glass. Is hot gas defrost available? It wasn't. These systems, by the way, we're training people. It comes across as it's new. They've been around a long time. There's over 40,000 of them in Europe, and they certainly have hot gas defrost. I think that's come up with just in the last few years. I'll be honest, I haven't been on a site with a hot gas defrost system, so I'm not greatly familiar with it, but you can just kind of think of it, as think of it similar to like a heat reclaim valve feeding a hot gas line. You're going to go reverse piping through the evaporator around a check valve. It's very similar to the hot gas defrost you would see on an HFC, but again, at higher pressures. So you have to temper that pressure before you send it to the evaporator, because the high side of the system, from the discharge of the compressor all the way back around to the high pressure valve, that's rated at 159 bar. The evaporators on the other side of that, they're at 59 bar. So there are some components necessary between the discharge heat that's available and what you send to the evaporator. It's a little complex, but very doable. Is parallel compression there for when you need more compressor load, or is there another reason? That's what we're going to jump into here in about 10 or 15 minutes. Short answer is it serves a different purpose. It's going to deal with the flash gas that builds up in the top of the flash tank. They're going to handle that load at a higher temperature so that we can have energy savings dealing with that refrigerant that's kind of already spent at that point. Can dry ice form during operation from inaccurate transducer readings? During operation, the answer would be no, because you're going to be about 200 pounds on your low temp side, not much below that. 200 pounds, I believe, is minus 22 or minus 20. And then you only go up from there. So flash tank is at 520, medium temp is at 400, and of course the discharge side, 800 to 1400. So you're never going to really see conditions of below the 70 pounds that would cause you to form dry ice.